right, so I wanted to create a video solution to help out. There's been a lot of questions in the group meet tonight related to rational functions. So I'd like to make a video to help explain this. Sorry, I see my videos freezing in the corner as I'm recording this, but hopefully that's working out okay. All right, so the goal here is to build a rational function, which is a ratio of two polynomials. So I'll go ahead and set this up as a fraction here, that has these characteristics. So we kind of have to think backwards where we're given the information. Well, I think about, well, where would that have come from in the equation? So for example, if the graph has vertical asymptotes at x equals -3 and x equals 3. So like I was saying, we have to think about where that came from. So vertical asymptotes correspond to zeros of the denominator. So I'll abbreviate here. So if say x equals 3 so 3 is a zero of the denominator, that would mean that x minus 3 should be a factor of the denominator. And if x equals -1 is a vertical asymptote, -1 is a zero of the denominator, which means x minus -1, which is equal to x plus 1, is a factor of the denominator. So I'll put x plus 1 down here. Okay, so we have that from the equations of the vertical asymptotes. Now the x-intercept, I'm going to use a different color. X-intercepts correspond to zeros of the numerator. So the fact that there's an x-intercept at 2 tells me that 2 is a zero of the numerator, and so x minus 2 must be a factor of the numerator. So once I put the x minus 2 there, then that characteristic is satisfied in this equation. Horizontal asymptote at y equals 0. So equations of horizontal asymptotes, this is what's been going on in the GroupMe chat tonight, has to do with comparing degrees of the numerator and the denominator. So real quick, a summary about how you find the equation of a horizontal asymptote. There's 3 scenarios to consider. You can consider the scenario where the degree of the numerator is equal to the degree of the denominator. You can think of that as a balanced rational expression, same degree on the top and bottom. When you have that same degree on the top and the bottom, then you have a horizontal asymptote at y equals a over b, where a and b are the leading coefficients. This is the ratio of the leading coefficients. I'm going to abbreviate here. So that's when you have same degree top and bottom. As a quick example, if you had y equals 3x squared over 5x squared minus 2x plus 7, then this would have a horizontal asymptote at y equals 3 over 5. You would look for highest powers of x on the top and bottom, take those coefficients. By the way, for those of you who understand things better when you know why that's true, horizontal asymptotes have to do with what happens when x gets really, really big in magnitude. So when x approaches infinity or negative infinity. And when that happens, the highest power of x in the numerator and the denominator, that's what's going to drive the behavior of the function when x is very, very large. X squared becomes much, much greater in importance than just x to the first power. And so this function essentially will behave like just y equals 3x squared over 5x squared. So when you have same degree top and bottom, same highest power, those x squareds are going to cancel, or whatever it is that's your highest power are going to cancel, and you're left with just the leading coefficients. So just if it helps to remember this rule, that's why it is what it is, because you're comparing, it's as x gets really big, the highest power of x takes over. Now, when the degree of the numerator is smaller, so less than the degree of the denominator, when you have a higher degree on the bottom, sometimes teachers call that a bottom-heavy function, then there's automatically a horizontal asymptote at y equals 0. And just off to the side, for you guys who want a reason why that's the case, let me take an equation like y equals x over x squared plus 1. Just something kind of simple. So if you think about as x gets really big, so those highest powers of x are going to take over. So let's say we're comparing x over x squared. Well, so that would reduce to 1 over x. And as x gets really big, this expression 1 over x, so think about 1 over 10,000, 1 over 20,000, 1 over 30,000. That's going to be 0. If you put that in your calculator, 1 divided by 30,000, you're going to have 0.000, however many zeros. It's going to be something close to 0. Okay, so just in general, higher power on the bottom, horizontal asymptote is y equals 0. And if the degree of the numerator is exactly 1 higher than the degree of the denominator, that's when you get these slanted lines as an asymptote. So you get what's called an oblique or a slant asymptote. Now that opens up a whole other discussion, so I'm just going to kind of leave it there. But in general, when you have a higher degree on top, when the higher power is on top, then there's no horizontal asymptote. You may have a slant asymptote that you need to figure out if you're going to graph it, but there is no horizontal asymptote. Okay, so that was a little bit of a sidebar there. But going back to this thing has a horizontal asymptote at y equals 0. Well, so horizontal asymptote at y equals 0 when you have a greater degree on the bottom, which we already have. This is degree 2 on the bottom. When you multiply this out, you'll have x squared in front. Degree 1 on top. So we can kind of check this off with what we already had. So now this f of negative 2 equals 3 business. So the deal here is we never ended up comparing leading coefficients, right? There was no like y equals 6 as a horizontal asymptote, so we put 6 over 1 in front. As long as there's a higher degree on the bottom, the horizontal asymptote's y equals 0. It doesn't matter if this is like a 5x on the top and then x squared on the bottom, or a 2x over x squared, or a point or a pi times x over x squared. You could have any coefficient of x up here. It's still got higher degree on the bottom, so it's still got that horizontal asymptote at y equals 0. So we really need other information to figure out the leading coefficients. If I put like a over b here, which I could summarize as just an a in the numerator, to have that kind of encapsulate the a over b. So, okay, you're supposed to use this information here to figure out the leading coefficient. Or if you want to, you could think of it as the ratio of the leading coefficients. And this is the part of the problem I really want you guys to worry the least about. The other information that we've covered so far, that's actually the really important stuff. But the way to resolve this last piece here, well, we could try plugging negative 2 in now and just see if does what we already have happen to work. Let's see. If you plug in negative 2 for x, you'll have negative 2 minus 2, so negative 4 on top. And then, what would this be? Negative 2 plus 1, so negative 1 times, this would be negative 5. You're not going to get 3 out of this, it looks like. So, here's what we can do. Okay, we can multiply this function by anything, and we would still have horizontal asymptote at y equals 0, vertical asymptotes at x equals 3 and x equals negative 1. X-intercept at 2, all of that stuff would be true with any number out front. So this is where we use, and I might need to erase a little bit here. This is where we use that function value f of negative 2 equals 3. Let me try to do this quickly. So if we plug in, oops, it's supposed to be a parentheses, negative 2 for x, I have a times negative 2 minus 2. Change all those x's to negative 2's. Negative 2 minus, this is supposed to be 3. Negative 2 plus 1. So this is negative 4 times a on top. Negative 5 times negative 1, so positive 5, right? and this is supposed to equal 3 as our output. So we want to solve for a so that this is equal to 3. So I would multiply both sides times 5. Erase a little, make a little more room here. If you multiply both sides there by 5, then you'll have negative 4a equals 15. And then divide by negative 4, and you'll have negative 15. That's supposed to be a 4. So that your final function is, sorry guys, I should pause and erase, but I'm not that sophisticated with my videos. Okay, so a is negative 15 over 4, and so our function, if I go back up here, actually that's what I should do. Change this a to negative 15 over 4. And there you go. There's your function that's going to satisfy all 4 of these requirements. Now I have to awkwardly figure out how to stop recording. Here we go.